So this is where we stopped in the last lecture, and I'll just, so now we know how to get from stars to light, if you make such a model. So one can put all this together, and one of the things that one would like to predict is what's called the luminosity function of galaxies. That is, how many galaxies are there at any particular brightness or any particular this thing at some wavelength that you observe. And then theory can be compared with observations. So this is what has been done, try to attempt here. The dots here are the observational points in some magnitude. Here it's the P magnitude here. And here it's the K magnitude. And this histogram here is from the theory of trying to put some light into whatever prescription roughly that we have, into dark matter halos to make galaxies. And you see clearly that this is more or less like almost a power law, straight line, whereas the galaxy luminosity function has characteristic scale, which you can try to match by playing around with the mass to light ratio, but the slope at both the faint end and the bright end are not fitting. By the way, this should be bright because it's ulta. There's a magnitude, absolute magnitude, so minus 24 is much brighter than minus 16. So these are faint galaxies and these are bright galaxies. And this problem was seen from about a decade or so back. For example, this slide I've taken from one of the early talks which by Simon White, and that's why I've referred to it. But these are the co-authors, and this paper, there are a bunch of people who noticed this and tried to fix it. And one of them is this paper by Croton et al. So what's gone wrong? I mean, we have tried to, let's say they have tried to do as best as possible to find a star formation rate, to find a star formation law, to find the luminosity mass function of stars, convert the stellar things to luminous thing, and it doesn't fit. So what seems to be missing still is now in the context of galaxy formation, effects of feedback. You over-predict both faint galaxies and bright galaxies. So you need to have some kind of feedback into star formation. And if you incorporate such a feedback, for example, here, these authors have incorporated feedback, which I'll explain each one of these, due to reionization, due to supernovae, and due to active galactic nuclei. Then, lo and behold, you can fit this luminosity function of galaxies. So you can just see that these two things, if I just scroll this, you just flatten both ends. You flatten this end and you flatten that end. So what are these feedback processes? So this is the next important thing in trying to predict properties of galaxies, that star formation, even if you figure out the star formation law, the initial mass function, even if you figure out the rate of star formation, you still have to figure out that given a galaxy which is forming stars, what is the consequence of this star formation, and in this particular case also active galactic nuclei in the centers of galaxies, on the galaxy itself. A simple thing, for example, this is a later study with huge number of simulation results now incorporating feedback. By the way, this is also a very nice reference by Torsten Naab and Jerry Oestreicher. And you'll see Jerry Oestreicher is figuring right from 70s when, at least in the galaxy formation context, when he's proposing the cooling criteria with Martin Rees, to today, when he's now probably 70 plus and doing all this stuff with now still extremely active, very nice review on the galaxy formation models and particular computational galaxy formation models. So several of the plots are from that review. And now you can see these observed points and these simulations are all not perfect match because to incorporate feedback into simulations is also not absolutely trivial, but it's doing not bad. In fact, one of these plots is from work by Nishikant Kandai and company, and I think he's coming here later, may come here later and give a talk. So, I mean, there you can hear it from the horse's mouth, so to speak. Don't tell him I called him a horse. So, what are these feedback? The first feedback is due to supernovae. And you have galaxies forming stars with a certain mass function of stars. There are heavy, high mass stars and low mass stars. The high mass stars will evolve fast, collapse, and if it's greater than about 10 solar masses, will collapse and blow up as supernovae. Some part of it will collapse to form a neutron star or a black hole and eject the rest of the material in an explosion called a supernovae. The supernovae are, will, if it, for example, I have something about supernovae here, yes. If you take supernovae feedback, then they create hot bubbles of gas. The hot bubble is because the supernovae is ejecting material at very large velocities, much larger than the speed of sound in the surrounding medium. When they gather up enough mass comparable to the mass of the ejector, they form a shock. This shock propagates into the interstellar medium. Across this shock wave, the gas which is coming in gets heated up roughly to the kinetic energy of the ejector. And that can be very hot gas at 100 million degree Kelvin and then cool down. And then the supernova evolves. So it creates a blast wave, a hot bubble of shock heated gas. And if you have many supernovae nearby to each other and they're clustered, these bubbles can sometimes overlap, like in the centers of the galaxy, and form superbubbles. Then these superbubbles of hot gas will not be confined in the galactic potential of the disk, and they will try to escape out of the disk of the galaxy. And they'll blow a wind of hot gas, and they will also entrain cooler clouds into the wind, and then they blow this wind into the halo. And here is an example of such an outflow from a star-bursting galaxy, nearby galaxy, called M82, a famous guy. And this is the disk, which is almost seen edge on here. And in the central regions, the gas is being ejected. And this in various observational bands. So you will not only have accretion of cold gas to form the galaxy, but if you have lots of star formation, the gas itself, because of the star formation, can get heated and ejected out of the galaxy. So it's a reverse process, and that's why it's feedback. For example, if you take a saltpeter mass function, you get about, for every solar mass of star, you get about one big supernovae, which has a luminosity in radiation of about 10 to the 51 ergs. I should say no. And if you take a different star formation, stellar mass function, where you have a lower mass cutoff of 1 solar mass, instead of 0.1 solar mass, which is the saltpeter one, you can see that there is almost a 3 factor of 3 increase in the number of supernovae that you can get per unit solar mass of stars formed. So the feedback also depends upon what is the initial mass function of stars that you assume. And these, if the energy is given to the supernova, in some amount of time, is equal to the binding energy. If the energy given to the gas by the supernovae is equal to the binding energy of the gas in this potential well of the galaxy, then it can completely get stripped and escape the galaxy. Long time back, Deckel and Silk made such an estimate and found that typically small mass halos, less than about 100 kilometers per second, will get stripped of their gas by the first bursts of star formation that you have. So for a given amount of gas mass, they will form less stars. If they form less stars, they are less bright. And if they are less bright, there are less number of them that you can see above a magnitude threshold, and they can explain this suppression at the faint galaxy end. The other thing which I'll come back to, which can also explain that at a higher redshift, is reionization. So this is one form of feedback. And this turns out to be fairly important, not only in this explaining the observed luminosity function of galaxies, but also explaining the basic properties of things like disk galaxies themselves. So let me spend a few minutes on trying to ask, how does a disk galaxy form? Okay? So we know, right in the first lecture, I said there are these two main types of galaxies, disks and ellipticals. And I mean, one of the goals should be, how does such a galaxy form? I already talked a little bit about getting angular momentum. These galaxies are guys which are supported basically against gravitational infall because they have angular momentum. The stars are all, and the gas and stars are rotating around the center of the galaxy in this disk. So if you have a gas cloud with angular momentum and it's cooling and falling in to the center of the potential, then you have this dark matter halo. So the initial state, let's say, is a very simple state. You have a dark matter halo, let's say, of 100 kiloparsec. You have gas filling this dark matter halo. The gas manages to cool, and as it cools, it loses pressure support. It falls into the centers of this dark matter halo. And it falls, as it falls in, if it conserves angular momentum, it will spin up. And it cannot fall in perpendicular to the angular momentum because of angular momentum conservation. But it can fall in parallel to the angular momentum vector. And so typically you will form a disk. The disk, typically this will happen when it's fallen in by a factor of 10 or so. And you have this disk. This disk is almost self-gravitating, not completely. The dark matter halo potential still dominates at the outer regions of the disk. But in the inner regions of the disk, it's just the gas potential itself which is going to get converted to stars, which dominate the gravitational forces. So you form a disk like that. But it turned out that if you do not have feedback of the kind of supernovae, then the first galaxies which form itself will form these disks, will form stars efficiently, will exhaust the gas supply, so that the later galaxy, today the Milky Way galaxy, which is pretty old and it has formed a bit much later, will not even have gas enough to sustain the disk that we see today. Secondly, it turned out that if you did not have feedback, the gas condenses more into smaller objects, and these objects then hierarchically cluster to form the big galaxy. They lose their angular momentum, and the gas itself loses angular momentum, and the disk that forms is too compact, has too many stars, and too big a bulge. So the simulations, which did not include some kind of supernova feedback, had great difficulty to make this that we see today. But if you do allow for feedback, then you get less stars in the beginning, and more of the angular momentum is retained by the gas, and you get better disk galaxies. And also it allows for a more extended epoch of star formation as one sees. For example, from the same review by Torsten Naab and Ostreicher, they have shown a bunch of simulators, which are all fairly recent, as you can see, few years old, which have all incorporated feedback into this galaxy formation and get reasonable looking size this that you see. What about elliptical galaxies? The elliptical galaxies popularly are thought to be formed by mergers of disk galaxies. Now, of course, you would imagine the ellipticals could have been simpler to form if there was no angular momentum. Then, of course, then you would not form the disk. All this problem which I'm telling about forming the disk would be favorable for forming the elliptical, things collapsing into smaller clumps, merging together, forming a bunch of stars, etc. But then you will only form ellipticals. So you can't have both things, the cake and eat it. So the way it works, way people work this, is that they would like to form this, and they do all the things to solve this galaxy formation, and then merge these galaxies to form ellipticals. And this also works out because when you merge disk galaxies, you form a more spheroidal kind of system. Of course, there has been a big controversy through the years, which probably is not settled, but probably people who are arguing have given up, is can you make really very compact ellipticals from merging disks? And one of the persons who used to argue very much against this is Jerry Oestreicher. Because, I mean, I remember this classic statement says, how can you make a rock out of dust or something? Because the ellipticals have such a large stellar density in the center that it looks very strange to take a bunch of stars from two disks and merge them. Because remember, stars are collision-less system. So they conserve what is called the phase space density, roughly. Even if you merge stars, you won't increase the phase space density a great deal. In fact, you would probably decrease the phase space density. And the phase space density in the centers of ellipticals could be large enough that it is difficult to make it just from disks. On the other hand, if you include gas, which can accrete and form more stars in the center, then you could increase the central stellar density. So this is not, again, completely settled, but roughly, the way in which people think about this galaxy formation is that this galaxy is formed. First, you acquire by tidal torques angular momentum, and then you form, it collapses to a disk, then you form stars. Now, the observed disks are also pretty thin, so you can't do violent things to it. For example, if you have formed a disk, and then you get another galaxy coming through it, it'll completely disrupt and disrupt the disk. So you need some quiet accretion of the gas to form bigger and bigger disks. Okay. Yep. Not yet easy to discern because the resolution is not so much. But you can do another thing. You can ask in the same redshift, like today, you see more disks or ellipticals as you go to denser and denser environments. For example, you go to groups and you go to galaxy clusters. And there you do see morphology density relationship. The denser, I mean, if you go to galaxy clusters, you see more ellipticals. And it's thought to be because more mergers took place, which converted disks to ellipticals. But going to higher and higher redshift requires resolution. And you see some blobs. Well, some of them may be disks, some of them may be ellipticals. I wouldn't bet my life on that. But it's an observational, a good question to address as you go to, for example, the next generation, the space telescope and things like that. Yeah, agree. So that's one form of feedback. And as I said, I won't come into it. The other form of feedback, which is interesting and which has been invoked to solve the problem of the luminosity function, and also another problem to do with galaxy clusters, is what is known as AGN feedback. AGN stands for, if you did not already know, active galactic nuclei. There is also a parallel part of the story of galaxy formation. At present, there is observational evidence that almost every galaxy hosts a central black hole. And it's fantastic, remarkable that every galaxy almost hosts a black hole. There's also observational evidence to suggest that the mass of this black hole is roughly 1,000th the mass of the galaxy. Our galaxy is a bit unusual. It hosts about 3 million solar mass black hole, but its halo mass is 10 to the 12, stellar mass is 10 to the 11. It doesn't follow this. But bulges, those guys which have got ellipticals or bulges, all host black holes. So one of the things which people doing structure formation or galaxy formation will be doing is following simultaneously the evolution of central black holes in galaxies. Now, the only way we really know how to make a black hole, if at all you know, in the sense, is stellar mass black holes. Because one knows that if you take a massive star, it blows up, and then it will either result maybe in a remnant neutron star or a remnant black hole. Nobody really knows how to make supermassive black holes in the centers of galaxies. Now, if it's 1,000th of the mass of the bulge or something. I mean, you can either make a mass correlation, or a better correlation is the mass of the black hole versus the velocity dispersion in the central regions of the bulge. Then what happens is this mass of many massive ellipticals, the black hole would be about 1 billion solar masses, not like the one which we see. So it has grown from maybe, so you need to make a seed black hole from some process, then keep on, every time it sits there, it keeps on eating stuff, becoming bigger and bigger and bigger and bigger, until you get finally at the end of the day 10 to the 8, 10 to the 9 solar mass black hole. We certainly see evidence for it in the local universe. We see evidence for active galaxies as you go back in redshift. And apart from understanding active galaxies themselves, which is a very interesting and important activity, okay? They're not just made for cosmologists to have feedback, right? So apart from that, they can also do this. For example, what is shown here is various resolution images in radio of M87, which is a nearby very active galaxy. This is the biggest, this is like 20 kiloparsec, this thing. So this may be, let's say, 100 kiloparsec. So sometime the active galaxy also emits jets, and these jets can be seen in radio observations. They emit synchrotron radiation. And in this particular case, the jet has filled out a whole lobes of relativistic synchrotron emitting plasma. And this kind of thing, if it's happening in the center of the galaxy, would do some damage to the galactic gas and maybe choke the star formation, stop accretion of matter if it's so wide field. And it can be traced, for example, in this particular context, to smaller and smaller scales. This is a VLA 20 centimeter observation. This is basically 1 meter observation, like GMRT, okay? 90 centimeter. There's 20 centimeter, and you can see some scale there. Then up to VLBA scales of 8 parsecs. Or sorry, this is what? 0.01. So fractions of a parsec, the jets are originating near the center of this galaxy at very small scales of the black hole. Remember that a black hole, solar mass black hole, the horizon is 3 kilometers. So if you take a 10 to the 8 solar mass black hole, it's few times 10 to the 8 kilometers, right? And that's like how much? 5. So 10 to the 13 centimeters. So it's pretty small. Okay? Then you have an accretion disk around it, maybe extending 100 times that, 10 to the 15, 16 centimeters. And then you have a jet coming from that region. And that jet is going to influence hundreds of kiloparsec kind of regions. And some of these jets are seen going up to a megaparsec, the biggest of these jets. So by itself, it's a fascinating object to study and understand. But what can it do? If you have such active galactic nuclei, where accretion onto a supermassive black hole results in various energetic phenomena, firstly, they emit radiation. Typically, about 10 to the 8 solar mass object will be emitting about 10 to the 46 ergs per second in radiation. They can have outflows, they can have jets. The radiation can hit and get absorbed by dust grains and eject the dust grain. That's one kind of feedback. The outflow can energize the region. For example, there are AGNs called quasars, broad absorption line quasars, which are seen to have outflows of 10,000 kilometers per second or so. Okay? The outflows which I was talking about in M82, the stellar mass outflows, will be 200 kilometers per second. So these guys could just throw away material. It's also been hypothesized and seen also that in centers of galaxy clusters, the blobs that you emit, the jets that you emit fill out blobs. These blobs become buoyant and rise, and as they rise, they generate sound waves. The sound waves can get dissipated by viscous forces in the galaxy cluster and heat gently. It can also stir the medium and create turbulence. Then something which I'm very fond of, cosmic rays, which are relativistic particles, can also contribute to various processes. I may come to that. Again, it's a very interesting subject, how exactly the energy from such a supermassive black hole gets channelized to bring about a feedback in star formation in a massive galaxy. There are various ideas. None of them are absolutely pakka, and but it's crucial for setting the largest galactic mass. So this part of the luminosity function, where you suppress the large galaxies and galaxy clusters from forming too many of them, too many stars, that part is thought to be due to such AGN feedback. The supernova don't have sufficient energy to do anything to that part of the galaxy. So you have AGN feedback, you have supernovae feedback, you also have reionization feedback. When the universe got reionized, as you have been hearing from other speakers, the gas also got heated to about 10 to the 4 degree Kelvin, which means that from a cold gas, the Jeans mass suddenly jumped, and it can no longer be accreted onto small mass objects. Okay? So there is also a feedback on the smaller mass objects from the fact that reionization heated the gas to a higher temperature. I won't talk too much about it. One of the interesting feedback which has not received so much attention is due to what are called cosmic rays. Now, cosmic rays sounds all like bizarre science fiction, but they are referred to what are relativistic charged particles. Now, I and one of my friends, Sri Anand, used to go for these walks, and I would keep talking to him about cosmic rays. He'll keep talking to me about photons. I would say protons, and he'll say photons. And both of us used to think we are talking about the other thing. Okay, because I tried to get him interested in this cosmic ray, and we wrote a couple of papers finally, even though we were talking about photons and protons. So these are relativistic protons. In a shock, you accelerate particles, and shock acceleration in the interstellar medium is very much like changing jobs and getting higher and higher salary. You tell your one employer that I've got a job there, so they raise the salary. You go there and say, I've got a job here, and they raise the salary. And you keep building up. Okay, and if you exponentiate sufficiently, you get a cosmic ray particle. And so these relativistic cosmic ray particles, which are accelerated in shocks, they have very interesting properties. Firstly, our galaxy, the pressure in cosmic rays is comparable to the pressure in all other stuff. If you have the interstellar medium, thermal pressure. If you have turbulent motion, the turbulent pressure, so to speak. If you have magnetic fields, the magnetic pressure, and the cosmic ray pressure are all comparable. So they are already an important constituent to support the galactic disk against gravity in our galaxy. Now, if you have a relativistic particle, I'm talking about a particle at least, let's say 5 GeV or something proton. That's where the maximum energy is. Proton rest mass is 1 GeV, let's say. And then you have at least gamma of 5. It's relativistic. Going at c, it will escape from our galaxy pretty fast because it's moving at c. The thickness of our galactic disk is about 500 parsecs, 1,500 light years. So in about 1,500 years, it'll whiz off. But cosmic rays, you can see, are confined to our galaxy to about at least 1 million years or so. And that's coming from, it knocks on other guys, produces secondary products which you would never have got otherwise. And by measuring the abundance of those, you can infer the time it spent in the galaxy. And they're confined because of, again, very interesting thing, that if you have this charged proton moving, and then that's gyrating on magnetic fields in some helical paths. If you have enough of them and they're going too fast, then it leads to an instability. And the electromagnetic fluctuations grow, which are also like waves, which are called, which are also having the same wavelength as the gyration radius of the cosmic ray particles. These waves can resonantly scatter off the cosmic ray particles themselves, and they slow them down. So there is a very close interplay, and when they are trying to slow them down, some momentum must be exchanged. If there's momentum exchange, the waves are giving it to the rest of the thermal plasma. So there is a very interesting interplay between the fact that you have all these relativistic particles, they are trying to go all over the place, they are coupled to the magnetic field and the gas, and then the waves transfer momentum to the thermal gas, you get a pressure gradient due to cosmic rays. And this cosmic ray pressure, as I said, is comparable to the gas pressure, and they can even push cold gas out of the galaxy. In case of supernovae and hot gas, if the gas is too hot, okay, it will be fine, but if the material is too dense, this gas will cool again. So even the implementation of supernova feedback into various simulations always had this problem. If they try to put a lot of energy in a very dense place, that place will cool and you will never get some energy going out. But these cosmic ray guys, they're not going to cool because they're relativistic. There is very little way of them cooling except by giving energy to the rest of the matter. And because they are protons, they are too massive to radiate easily their energy. Because you know that all the cross-section go inversely with mass, like the Thomson cross-section. Electrons can radiate. Protons have more difficulty radiating. And so they're absolutely fantastic. You have them for free. So only now, recently, in the last half a dozen years or so, many more people are incorporating cosmic ray physics into all the outflow models that they're taking into account. Okay? So this is another feedback. But some of my friends had already done it about 10 years back, and they looked at its dominance, whether it's dominating in voids or clusters. For example, this is the E energy in cosmic rays to the thermal energy in a large-scale structure formation simulation. And basically, you don't get much in structures, but they can dominate in void regions. But I'll come to that. Yeah. The other interesting feedback, not feedback, but player in the game. Yeah, I said the pressure is like comparable. The energy, since they are relativistic particle, pressure is 1/3 the energy density, roughly. And so the energy density will be comparable also, compared to thermal energy. Yeah, 3 times. Yeah, in fact, there's a lot of interesting stuff you can think about. So are magnetic fields important? How can I give 3 talks without mentioning magnetic fields? And somebody said, this guy, why are you not talking about magnetic field? I said, okay, I know other stuff also a little bit. so, right. So why? I mean, already I've told you that without these magnetic fields will actually influence all this stuff like cosmic ray feedback. But there are other stuff which is very important with and without magnetic fields. For example, how do you know that your gas is a fluid? Now, you know if it's a fluid or not, and make the approximation saying that the mean free path is much smaller than the scales you're interested in. Many times this works, but in certain circumstances it doesn't work. An important place is galaxy clusters. The mean free path for particles due to Coulomb collision in galaxy clusters can be of order of kiloparsecs, several kiloparsecs, at the density and the temperature that you have. But many processes are occurring, which we assume that the mean free path is like minuscule. Okay? Now, without the presence of magnetic field, the magnetic field can give you fluid-like property to this hot and dilute plasma. Of course, you should have the field to begin with. Because firstly, there will be all kinds of instabilities in the presence of the field, which will give you small-scale electric and magnetic fluctuations, which will resonantly interact with particles. So Coulomb collision will no longer be the relevant transport, the process of collision. Secondly, the field itself confines everything. It's very difficult to cross the field. Because you try to cross, there's a Lorentz force, V cross B, which will turn it back. So at least along field lines, you're more or less confined to the gyro radius, which is much smaller than these kiloparsec kind of scale. Okay? But it also affects all transport processes. If you really have that large mean free path, you get very large thermal conduction effects. You can get very small viscosity. You can get very small resistivity. All these transport processes are quite important because they will transfer energy, momentum, and current. They dissipate energy. I mean, the viscosity will dissipate kinetic energy. The resistivity will dissipate currents. And the thermal conduction will allow different temperature regions to communicate with each other. You may like this, you may not like it. You may not want it to communicate. But then none of these transport processes are well understood in such dilute plasma. So it also controls that these processes become non-isotropic. Of course, magnetic field is good and bad. Bad because people don't want to live with it because, I mean, it complicates your life so much. Good because it may do other things for you which you are assuming at present. And there is a whole question of how does it control star formation? Present-day star formation, which occurs in molecular clouds, is completely dominated by magnetic field effects. The fact that you get jets is because of magnetic field. Whether you get support or not is because of magnetic field in the molecular cloud. Okay, so if you don't have it at all, if you did not make it at all in the universe at some stage, you don't know how exactly star formation will occur. Because the only place where you see star formation explicitly, nicely, in a controlled way, is our galaxy in molecular clouds where things are already important. So there are jets, as I already said, cosmic ray, confinement, and of course, it's fun to think about. So that's just a small advertisement for thinking about magnetic fields, and it ends. But people have still, of course, done various of these feedback processes, and there are now the newest bunch of such simulations are called the illustrious next generation. So this, I think, from a movie, I guess, and it's called TNT. Movie or a serial? Huh? Star Trek, yeah, of course, shit. Star Trek, the next generation, yes. Yeah, that's the younger generation. So, so you can see a whole bunch of disk galaxies from the simulations looking not very dissimilar to what one sees. It turns out all these guys are about 10 to the 12 solar mass, and they have this variety. You can also see a bunch of ellipticals, and you can look at this paper by Nelson, which is one of the earlier papers which has come out from this. They're also able to get things like galaxy colors, okay? And it's a massive, kind of very messy plot. I won't even try to explain it. But one bottom line is the AGN feedback I was talking about in something which is called the kinetic mode is important. Kinetic mode is where you give this feedback by injecting kinetic energy into the gas particles than just radiation. And they have even incorporated magnetic fields. Okay, they're learning. It's good. Okay, so that's about what I wanted to say about all the other people's stuff, in the sense that I think what I've tried to give you is a flavor of the physical processes that are involved in galaxy formation. Now I want to slightly move to some stuff which we have kind of tried to think about. I mean, can we put together in a very simple model these various ideas I've been talking about and come out with our own version of some galaxy formation stuff? So there's a whole bunch of papers. There were Sri Anand, who I've already talked about, and there is Shomadip Samvi and Charles Jose, who worked with both of us, like our students. And both of them are now gainfully employed. But in Presidency University, Shomadip is there and Charles is there in Cochin. And they have stopped working on these things a little bit, but of course, they're still doing some stuff. So the questions that we were interested is to do with high redshift galaxies. So this will also connect to some of the high redshift galaxy stuff which is going on recently. So you see galaxies, but this luminosity function which I showed you was the luminosity function at redshift 0. The simplest thing you can do about galaxies is to count. And that's what the luminosity function gives you. How many galaxies are there in a particular wavelength bin per unit volume, okay? And then you're trying to understand that. This has been expanded drastically by what is called the Lyman break galaxy technique. I showed you this spectral energy distribution. There is a drop at the Lyman alpha line, okay? This is due to absorption by hydrogen. Now, if you take a high redshift galaxy, here the picture is at redshift of about 3.15, then, and you have various filters. Filters means various observational windows in wavelength where you try to image the bit of sky that you have. Then it can turn out that in this filter there is no flux, and in this filter there is flux. So here there is flux, here there is flux, and here suddenly it drops out. So you can get roughly an idea of what redshift this galaxy is by having a whole bunch of these windows in wavelength and measuring that flux in these windows and saying at which filter it drops out. Here, you expect the dropout to be at the Lyman alpha wavelength, and here it's at 4,000, and so you infer a redshift of about 3.15. So this is a photometric redshift, where you get a redshift by just counting photons in different wavebands, but not by taking a detailed spectrum of the object. Of course, then you can go back and try to confirm whether such objects really have this redshift or not. It turns out that this technique, which was invented now some time back, even has been extremely useful to find higher and higher redshift galaxies. So that there's a plot even at 2012, there are these luminosity functions. I didn't update this plot, I could have. Available up till here redshift 8, now you go up to redshift 10. Some of them are much better constrained, some of them are not so well constrained. So this is one kind of observation you have already about the high redshift universe. And one would like to understand, can you explain this observations of abundance of high redshift Lyman break galaxies? Okay, that's one question you can ask. The other kind of observation which I will show, which may be here, for example, later. I added this because Aseem said it may be interesting to show this, is the clustering of such Lyman break galaxies. That's also available at different redshifts. Here it's shown at 3, 4, and 5. So just like the 2-point correlation function which you measure in the local universe, you can also ask if you have this complete sample of Lyman break galaxies and you have it in some particular area, are they randomly distributed? Are they clustered? If so, what is the angular correlation function? And can you understand that clustering of the Lyman break galaxies? And since there has been some discussion about halo models in the previous lectures, Aseem thought it may be interesting for me to mention it again in a different context. So these are the two things which we wanted to understand. And these were the two things which this bunch of papers and some more which I didn't add were trying to understand. So we wanted to understand the high redshift Lyman break galaxy luminosity function, the redshift evolution, the clustering, and we also threw in a nice spanner in the works, which was always nice. Can you use this to constrain something else? So this is also a paper which Charles was the main author. We weighed neutrinos using this high redshift luminosity function. I will not talk about that in great detail here. I can mention it later. So built a simple model, for example. The assumption is that galaxies form in dark matter halos. There are abundance of the dark matter halos. So we were not going into simulations too much. We are not going to either numerical simulations too much or into the whole industry of semi-analytical simulations too much. Firstly, because I can't simulate, the students could. But we thought, let's try to understand in a very simple-minded model. So we used a lot of framework which is already developed from analytic or semi-analytic kind of framework. For example, you heard about the projector theory. That will give you abundance of halos, the number of halos of different masses. Now you have to populate those halos with galaxies. For that, you need star formation. And so we made an assumption that the star formation basically, as I said, decayed exponentially in time over a dynamical time scale, but also rose from zero over a dynamical time scale. Later, Shomadip tried to model this much better by putting in accretion rate, etc., etc. But to begin with, we just started with a simple model. And a fraction of the baryons got converted into stars, which is this F star. And the Lyman break, the observations are all at something like 1,500 angstrom. So we need the luminosity at this wavelength, and that is got from a publicly available code called the Starburst 99, which, if you're interested, there are many of them available. This is the one which we use, where you can actually give what is the IMF that you want to assume, what's this mode of star formation you want to assume, and you'll get a whole bunch of luminosity, time evolution of the luminosity at various wavelengths. And you can do this convolution if you have this model. And then you need observed luminosity. It need not be this, because there's always dust extinction which you do not know. So that's also a parameter. So there is one parameter which is this F star by eta. Then you convert luminosity into absolute magnitude, and people quote it in the AB magnitude. And this parameter determines the light to mass ratio. And galaxies of different masses forming at different redshifts can all have the same luminosity at some redshift, because they may have age by different amount, and they may all come and have. So you can put all this together. Now you need to go from the projector or some other mass function to the luminosity function. So firstly, you need to know the rate at which you form halos, because that's the rate at which you will form also the stars in these halos, apart from the star formation in an individual halo. Only for the projector this has been worked out, and by a guy called Sasaki. And it has been worked out in some self-consistent way. For every other thing, you take, let's say, the time derivative of the mass function, and you can get some idea of the rate. But for projector, it's worked out. Then you have various Jacobians. You have to go from mass to luminosity, luminosity to magnitude. And so you have various, an integral over redshift. All these steps you can do without ever going to a numerical simulation. Okay? And you predict the luminosity function. Then you need to incorporate feedback, because we know that feedback is important. To begin with, in the early papers, we thought high redshift, let's only turn on the reionization feedback. In later paper, we have now tried to look at the supernova feedback and the AGN feedback. So roughly like redshift 4, for example, this is what you would get for some particular F star by eta. And it will miss some points here, miss some points here. You put feedback and you will get everything going through. So you can do a chi-squared fit, for example, in this. If you change your F star by eta, you will change this function here and there. So qualitatively, you are able to explain to quite surprising level of degree. And we are also able to make interesting statements about the level of star formation that you require and what is the importance of feedback. For example, for redshifts higher than 4, you don't need AGN feedback to explain the present observations. Okay? And one can even go further, and more recently, Shomadip has gone berserk and tried to fit all the redshifts right from 1.5 to 8, for which observations are available. The only qualitatively new feature from our earlier papers is that some of these luminosity functions are showing an upturn at faint magnitudes. For example, this at lower redshift. And these observations this faint magnitudes cannot be easily seen directly. They're coming from lensing observations. That you have galaxy clusters or something, some lensing object through which you're seeing these high redshift galaxies and amplifying. So they are uncertain because the amount of lens magnification is not a pakka thing like that. So there's a bit strange, but we never expected this upturn. And for this, we had to add a new ingredient in the system, which is to do with the fact that there should not just be a burst of star formation over dynamical timescale, there should also be a passive mode which lasts for a long time. And that dims galaxies and brings some of them into this regime. So there's a new stuff which we have added, which we have not yet published. And you can also do similarly clustering. So you again assume, as I said, dark matter halos have galaxies inside them, and the halo, and you have the biasing models, which I think have been discussed, that there is the halos are not, clustered exactly like the dark matter. They are biased with respect to the dark matter distribution. It's also important to know what inside a halo, one galaxy could be the central and there could be other satellite galaxies, and how many satellite galaxies, how bright they are. That's also important. Since we have a calibrated model for the luminosity function, we have a calibrated prediction for the central galaxies. If it's certain brightness, which halo it will sit in, it will be sitting in. You also need what people call the HOD, halo occupation distribution of the satellite distribution. For that, we tried to model it again by saying that satellites in subhalos collapsing in the parent halo before some time survive. So the same projector theory also gives you what is called a conditional mass function. Given a halo of mass m, how many smaller mass halos of a different mass can form in this? Was that also discussed? Not too much, okay. So there's a one step more. So you can predict how many smaller mass halos form when a bigger halo is collapsing. We have a scheme for putting luminosity into these halos. And now we said that, okay, if this formed before some time before the final collapse, it'll survive as a satellite. And so we could predict, at least with all our parameters, what this halo occupation distribution is. And then you can work out clustering basically between galaxies in different halos and within the same halo. I learned all this formula from some notes of Aseem long time back, which is somehow it percolated, I don't know how. Okay, so we could use all those formulas. Maybe I didn't learn, Charles learned, because nowadays I've become an observer. I observe other people doing work. Okay, sometimes you should also do work, but mostly you're observers. So this is the halo occupation distribution that we predicted, that you can see the number of halos versus, the number versus the mass, and it will look qualitatively similar to any of the other stuff that people kind of bandy about. And these are the, using all this technology, we've fitted all the clustering by this single halo term and by this satellite central clustering term. Most of the time we found a good fit, but many times we found that we could never explain for the highest redshift and the brightest galaxies an intermediate range of distances. Now, at large scales, linear theory is good. At very small scales, nonlinear theory is understood. To the way it's understood. Linear theory, biasing and all that, a lot of work has gone on. At very small scales, there is spherical model, there is redshift, there is nonlinear evolution, which you can predict various things. It's always the middle, which is very difficult to understand. When things are neither linear nor nonlinear, and they're becoming linear, the quasi-linear regime. So we suspected at that time that something must be happening at the quasi-linear regime. Good. And so to learn what is happening, we sent off Charles to Durham to work with Cedric Lacey and Carlton Bow. And they had access to a large number of simulations. And he found what is the bias, what is called the nonlinear bias, especially in the quasi-linear regime. So they wrote a nice paper on that eventually, but eventually I extracted my pound of flesh, saying that now you use that to see whether this can be understood or not. And it turns out it can be. That if you incorporate the effect of the nonlinear bias in the quasi-linear regime, now yes, this is also from Charles. These panels have now gone up, by the way. So you can kind of go through all the points. If you don't incorporate them, you get this deficit. But of course, now we get a slight problem in the lower redshift and fainter galaxies. Okay? So the truth is not completely there yet, but you can understand the Lyman break galaxy clustering with the same technology that people have developed for the local clustering of galaxies. You have halo-halo correlations, you have satellite central galaxy correlations, you have some prescription for populating these halos with light, with galaxies, and that's it. So, end of the big katha for you. Just to summarize, I think what the kind of stuff that I have tried to talk about is that galaxy formation is a very interesting subject which has lots of physics questions, astrophysics questions, links between different fields, which all you should kind of learn about at some stage or the other. And what I've tried to emphasize is, for example, these few points, that efficient cooling sets the mass scale of galaxies. I kind of talked a little bit about the cold versus hot mode of accretion. Understanding star formation is key to understanding galaxy formation. I think if I kind of got you interested a little bit in star formation, my task would be over today. There are all kinds of interesting feedbacks, radiative, chemical, kinetic. They're all crucial for galaxy formation, as we saw. Things which are not yet very well explored are things like turbulence, magnetic fields, cosmic rays. People are just beginning to come onto this because they've exhausted other things. You have to keep doing stuff. And the new works are all trying to concentrate on the new simulations, on magnetic fields, on cosmic ray feedback. And it's this mess which is galaxy formation, which makes it interesting. Thank you so much for your attention for all these 3 lectures.